I would like to welcome everybody. This is a great turnout today. So this is, of course, the OSG Virtual School 2021. And it seems like there's a few different groups to notice here. So we've had some people who actually applied for the school in 2020, right before the pandemic hit, and ended up having to defer until this year. So they're joining us for the first time. We've had applications from this year that we accepted. And then this is a first for the OSG school in the, 12 years that I've run it, that we are allowing people to register and come participate in the lectures. So we're really excited to be able to do that. In some ways, the virtual format makes that more possible than it would if we were doing this in person. So welcome to all of you. And I have just a couple. Lauren's got me here as a presenter on this, but really I'm gonna talk for one slide and then it's all her. Lauren, if I could get my one slide, the one with more stuff on it. Yep, there we go. So just a little introduction to kind of why we're here today, both us and you. So we like to believe, since this is our business, that many people need access to large-scale computing in general, and in particular a style that we call high throughput computing, which is going to be the topic of this lecture. And either you're one of those people or you're the kind of person who is supporting researchers who need this kind of computing. There's going to be a lot of technical, sort of conceptual and technical detail over the course of this week. And so I don't want to sort of get into that too much, but I really want to plant one seed now up front. And I want you to be thinking about that throughout the week. And it's this what I have in bold here. Don't let computing be a barrier to or block your research. These days, by all historical standards, computing is incredibly cheap and plentiful, bordering on what feels like infinite capacity at times. And so in theory, with all this computing capacity available, your science, your research, or that of those you support shouldn't be blocked by needing access to computing. So we want to encourage you to push the limits of what's possible. In particular, of course, with computing and research. So if you feel like you're running out of science to do, if you've set out this program of computational research work and you're kind of getting to the end of it, think about where you could go from there, right? Transcend the boundaries of your science. And I mean, that sounds grand, but we've had the fortune, just in the last even 10 years of seeing this happen multiple times with different groups and different domains. And it's really exciting. So think about ways in which you could use more computing and do more interesting and new science. And then if it happens that computing actually becomes a barrier, like you've defined some computing and you can't actually make that all happen, push us to fix the bottlenecks or the problems that prevent you from getting that done. Most of the development that in HD Condor, which is the software we'll be talking about, and OSG, doesn't come from us just making up features and implementing them. It comes from real problems that people have in the field that we have to find solutions to. And so work with us to identify what you need and to figure out how to solve those problems. And let's see what we can do together. Now, can I sit here and promise that we can solve every computing problem and actually have what looks like infinite capacity? No, not quite, I can't. But you'd be surprised at how much we can do. And especially the more that we work together and the more that we engage each other, the more we can do. So keep that in mind. And then as you're learning more and perhaps putting more of this into practice yourself, please help and encourage others who maybe just haven't heard about high throughput computing and what it can do. This may be as simple as another member of your lab, all the way out to folks in your field, friends in other fields, and so forth. But we find that we don't run a big advertising campaign. We don't go out and try to tell people all the time about what we do. So word of mouth helps us a lot, kind of get the word out there. All right, and that was the seed I wanted to plant. And with that, I'll be quiet and let Lauren actually explain this stuff.
All right, thanks, Tim. So Tim and I co-direct the OSG school. I lead research computing facilitation at UW-Madison and for the Open Science Grid. And I know there are probably a fair number of research computing staff on the call today, so you may also know me from my role with some efforts that organize communities of research computing professionals. But in this first day of the OSG school, our lecture really here is an overview of high throughput computing and the Open Science Grid. So we're hoping that you leave with a better sense of what is high throughput computing as an approach, and what is the Open Science Grid as a computing system that enables extreme amounts of high throughput computing on a distributed scale, and how you can get the most out of the above in general, which leads us to a final discussion at the end of how the school content is organized for lectures through the rest of this week. And since this is the public version, I'll talk a little bit more about how those of you who are not enrolled participants this year and who are invited to join us for these public lectures in the first week, I'll talk about other features of the school that may be of interest to you if you'd like to apply in the future. But first, let's talk about high throughput computing. When we like to use the analogy of the world's largest cake, this is actually a picture of what I think is still the reigning world's largest cake. It was made for the Las Vegas centennial or 100th anniversary of the Las Vegas city. And if you're paying attention, I am going to ask you to chime into the chat a couple of times during this presentation. But how do you think they made the world's largest cake? And you've got two options. One, you can say they made a really large oven, or two, you can explain something else they might have done to make the world's largest cake. So I'll watch the chat and look for some brave souls to weigh in on whether they think it was a really large oven or they did something else. And I'm seeing some really creative descriptions that are all bake lots of cakes and put them together. And you're absolutely right, because it's not exactly practical to build a really large cake. But in computing, if we think of computing tasks as something like the endeavor to build a really large cake, we even have the analogy of ingredients being input files, for example, or instructions for computation, recipes being the software that puts it all together, or that gives results of, in this case, individual cakes. And it's very much the case that for the world's largest cake, they used run-of-the-mill ovens. They needed to use quite a few of them and built run-of-the-mill sheet cake size cakes, and then assembled them together, as you see in these pictures, into the world's largest cake. It was actually really large. It filled the whole gymnasium. But there are a lot of research problems that at their core look like this and can be most practically executed as lots of relatively small computations that can then run on a much larger number of computers that we might think of as being sort of run-of-the-mill ovens, rather than thinking of needing to run them on a large supercomputer cluster, a single monolithic kind of oven for computing. Now, when a lot of researchers come to people like myself who facilitate research computing, most commonly they're outgrowing their current research computing resources because things take too long. And frequently when we talk to them, that's because some aspect of the way they're executing things is done serially, meaning that they may have lots of images or pieces of data or parameters to compute. And they're doing these one at a time, maybe on a laptop, even on a server, but sort of looping over a different set of input instructions or data pieces. And so the overall compute time can grow significantly if the number of tasks increases, or if the individual tasks get more complicated, which is what we want when we want to tackle bigger research problems. So how can you speed things up? Most people, and it's okay if you're not, but many people are familiar with the term parallelize, which means to distribute the work across multiple computers, or really multiple cores or processors that might be on the same computer, if you've heard those terms, cores and processors. With a high throughput computing approach, if you've got lots of tasks that are self-contained or can be executed in a self-contained way, such that they each have their own input and output, which can, be analyzed or then produced from the same piece of software, you could run lots and lots of tasks, each on a different processor, even a different single processor. And so that's where I've drawn these as not being connected to each other anymore. They can be run completely independent of one another. And like I said, a lot of tasks naturally break down this way. This contrasts, though, with a term that maybe more of you have heard of versus high throughput computing, which is high performance computing, which from sort of a computer science theory perspective is more concerned with speeding up computation within a single execution. It tends to be a really useful approach if you've got large physical simulations that cannot be broken up into pieces. And that may be because a large simulation of something like a galaxy with billions of stars, or a large biomolecular complex with hundreds or thousands of atoms, might have multiple time steps of that simulation to progress through. And it's only within each time step that calculating the positions of those components, atoms or stars or whatever, can be distributed across multiple processors. Each processor or core can be tackling a subset of those, but they need to be communicating with each other, those cores and processors, so that in the next time step, each atom knows how it's affected by the atoms surrounding it after they've progressed from the previous time step. And so there are a number of applications that really require high performance computing and as an approach to parallelization, with internal parallelization, internal to a single execution. And high performance computing, by its title, is concerned with enhancing the performance of a single computation and building computing resources that enable that. So high performance computing, or internal parallelism, tends to benefit from homogeneous CPU speed, so speed and consistent speed across cores, so that some aren't waiting on others or falling behind. They often need access to shared file systems so that all of the processors or cores, even across maybe multiple servers, can access data in the same locations. They also tend to benefit from or require fast, expensive networking like InfiniBand, which some of you may be familiar with in the context of traditional HPC cluster configurations. The execution of the work from the user perspective requires special programming, multiprocessing or multi-threading as it's referred to, or MPI, which is message passing interface. That's the most common approach for running a single computation across multiple servers, where you need message passing between all of the cores on those different servers, where MPI gets its name. It's not trivial to program in these approaches, especially MPI. And if your work doesn't require it, there are also some other downsides that come along with scheduling these sort of fewer, larger computational tasks on a shared system. For example, you've got to wait until all of the processors you need to run a simulation are available at the same time and for the full duration. And there are some downsides in terms of failure. For example, if one core or server fails, and again, I'm going to ask people in the chat, what happens if you run a large MPI task and one server or one core fails out of all of them that are contributing? And then the chat, those of you who've experienced this can comment. What happens if you run a large MPI task across multiple servers and some of the cores or servers crash or fail? Synchronization error, says David. The entire process fails, says Scott. That's very much the case. And very true. Basically, the whole system relies on the ability of all the components to communicate with one another. And if one of those goes down, the whole thing fails and you have to start over or resume from some sort of recent progress state. If you've got work that doesn't require this, though, if you've got work that breaks up naturally into lots of self-contained computations, there are some significant advantages. From a scheduling perspective, if you break things down to each job in a set of them now, running on one or a few cores, you've got a shorter wait to get any of those cores running, any of the cores available to you, instead of waiting for a whole bunch of them to become available at the same time. If you submit a bunch of tasks to a shared computing system, as resources become available, your jobs can start to ramp up and the total number of cores you use can increase over time to some sort of steady state, according to, say, your fair share of that shared resource. There's easier recovery from failure. If one of your jobs or even several of your jobs are on cores or servers that have problems, or a network disconnection or a crash or something like that, the system could even detect that that's different from a code failure and just requeue the jobs and run them again, not affecting everything else that gets to continue running. There's no special programming required in these cases, especially if we're talking running lots of single core tasks. We've got researchers who come from their laptop using a single core code that loops over data. They can move right into just breaking out of that loop, running that same code with different input or parameters each time. And the computing systems that optimize high throughput computing make it really easy to express that in terms of submission without having to write really complicated scripts that can communicate a large number of tasks. The number of concurrently running jobs becomes more important to overall throughput, and the individual speed of different cores and certainly homogeneity become a lot less important. If anything, you could handle, each of your jobs taking a little bit longer than if they were part of some big set within an HPC approach. If you get to run so many more of them, if you could have many more cores in use concurrently, because that's really what ultimately determines your overall throughput and therefore your research impact. The example of a local computing system that our enrolled participants in the school get to use is the Center for High Throughput Computing's high throughput computing system at UW-Madison. And Center for High Throughput Computing is where the Condor scheduling software was developed, where high throughput computing as a term and a theory was defined decades ago and to this day. And we also serve as the Core Research Computing Center. We have a large high throughput computing system scheduled with Condor. It handles up to many millions of jobs in the queue at a time, large numbers of cores, and individual users can get up to 15,000 core hours per day if their jobs are in the form of single core jobs, because they can get up to 600 cores in use within hours of submitting. And not only that, we've got people running multi-core jobs, high memory jobs and servers there. Our GPUs are all there. Basically, we run anything there that can fit on a single server or less that doesn't require the specialized configuration of our smaller HPC cluster that is otherwise backfilled by the sort of smaller jobs in our high throughput system. There are a large number of computational research examples that run really well with a high throughput computing approach. In fact, if they can at all, there are significant advantages over using internal parallelism or HPC approaches. This includes text analysis, because individual pages, even lines of text, even individual genomic reads, since genomics is really a form of text analysis, all of that can be broken up into lots of independent pieces to really accelerate the rate of data processing. We work with a number of people across research domains who do some form of statistical model optimization or parameter sweeps, where there are a large number of computations that need to be repeated with different starting parameters or starting conditions. Similarly, we've worked with people who may run singular high resolution simulations of weather or galaxies, or some of the other examples I mentioned, like biomolecular simulations, airflow through a barn. But we also work with some of the same groups, same researchers, who occasionally need to run something at lower resolution or for shorter durations with different starting conditions, kind of like the idea of a parameter sweep. But sometimes this is like they're simulating different behaviors across different geographical regions, and each region can be simulated independent of one another. And then another popular one, especially in medically relevant research, is anything to do with multi-image or multi-sample analysis. So of course, it occurs in the life sciences too, with overlaps with genomics. But we frequently run into situations where medical scans are really a series of slices of a brain or a joint or something like that. And each of those images can be processed independently, and then the results summarized at the end. So these are all really great examples of high throughput computing work. From the computational perspective, and if you're research computing staff, these may be things to look out for to find people, even on your local clusters, who seem to be running fine, but could be running in a high throughput way, and therefore benefiting potentially from the extreme capacity of the open science grid that I'll talk about later. But anytime a researcher mentions numerous samples, images, models, parameters, I probe a little bit more to see if those can be analyzed independent of one another. Nearly anything written by the user, especially if it's in languages like Python, R, or MATLAB, at best is going to be using some internal parallelism, but that's a good sign that that user could break out of that loop, say it's a MATLAB par4 loop, and instead run lots of independent tasks for greater scale. Some community softwares that use multi-threading or multi-processing or even MPI are simply looping over data portions or independent tasks. For example, I've mentioned genomics several times, but I bet many of you, especially if you have any life sciences experience, are familiar with the BLAST read mapper software and other read mappers. But you may not know that you can break up a very large file of FASTQ reads as small as individual reads, run those with BLAST independently against the same reference, and literally concatenate the results, and you will get the exact same results as if you ran one big BLAST job that had to wait for a long time in a queue. And we've got really good examples of people doing exactly that type of work with other types of genetic analysis. And then the other sign would be long-running jobs, which generally means that some aspect of one of these things above is at play. But we also have a self-checkpointing bonus topic early next week for people who are enrolled participants. And otherwise, that's a feature of most high throughput computing systems because they already otherwise have things built in to handle job interruptions and at least requeuing, if not the ability for users to build in a resumption capability in their jobs. So let's take sort of one kind of real world example and scale this out a bit. Let's say that you've got 72 brain images or sort of slices for each of 168 patients. That adds up to around 12,000 compute hours. And you've got a conference next week that you want to present the results at. Here's some different distributed computing approaches. First off, if you were to do this on your laptop, not so distributed, you'd need 12,000 hours, which is about a year and a half. Clearly, we don't have that much time if our conference is next week. Let's say we had a server that had 40 cores. That still only gets us down to 2 weeks, right? And maybe we're okay waiting that long. Maybe we're worried that things would get interrupted and we'd not know how to resume or restart because we didn't break things up into separate pieces that could be tackled or fixed individually. If you had this organized as one large MPI job with 400 cores, it would take a little over a day, but how long are you going to wait in the queue? Is your code already capable of running with MPI? Or even if you ran this as lots of 40-core jobs, multi-threading? And what's your experience going to be in a large shared computing system that you might have access to, especially if you're an academic? But if you had access to the capacity of a whole cluster, 10,000 cores, you're now cutting this down to be about an hour of work once it's all queued. And I'll show you in just a bit that you really can have that many cores in use on the open science grid. So let's talk more realistically here. What computing resources are available to you out of that set? If you've got a server, that might help you speed things up a little bit, but maybe you're already outgrowing that. A lot of campuses have local clusters that are a really valuable resource. But if you're going to attempt a high throughput computing approach, most HPC clusters may be harmed by submitting lots and lots of jobs. Their queues may not handle that well. The queuing software itself, the file systems often don't do well with lots of jobs writing to highly numerous files. And maybe you could use even more capacity than is available on your local cluster. The OSG is a resource, and that's why we have the school to help teach you about that. But outside of that, there are other options. Maybe if you're in Europe, there's EGI, which is sort of like a high throughput computing system for Europeans, whereas OSG, though worldwide, is really heavily supported and participated in the US. There may be other national and regional grids available to you, depending on where you are in the world. And there's certainly cloud systems, commercial cloud systems available. For example, the Condor scheduler that is optimized for high throughput computing is available in various forms on AWS. You can build your own pool, you can execute work on AWS through Condor type submission. And a lot of cloud providers have some other form of high throughput computing execution that's based heavily on the decades of research invested behind Condor and other large scale grid systems developed in academia. Let's talk about the OSG and how it's a little different. The OSG is a consortium of researchers and institutions who share compute and data capacity to enable distributed high throughput computing in support of open science. So it tends to be participated in not by members of industry who are not doing open science, are often doing proprietary science. And that should tell you a bit about who's participating, but let's talk about that. Researchers themselves use computing and data capacity across the open science grid. Science gateways use it. So there are a number of science gateways, if you've heard of that term, where researchers can go to a really easy to use web interface, upload some inputs or some instructions, and then those get computed on some backend resource that might be a cluster at a campus or might be a nationally available cluster, but some of them use OSG as their compute backend. And then results are delivered back to the user either through that web interface or email or something like that. But by and large, the entities that contribute resources and share resources to enable researchers and science gateways are those at academic institutions and national laboratories that support research communities, including multi-institutional collaborations. And those include some major physics projects that have been part of the OSG for some time, operating their own virtual clusters within it, like those that discovered the Higgs boson, IceCube, the South Pole Telescope. Some of these have been in the news lately, especially for Nobel Prizes. But campuses are really critical to OSG's ability to advance research because they make up, by and large, the largest number of sites that contribute resources somewhere into the open science grid, often by collaborating with the researchers they support, who maybe are part of a collaboration or who care to have access to the capacity. So just to talk a little bit more about what the OSG is and how it's organized, there are a number of research communities served by these campuses and national labs that have organized computing and data capacity for themselves within their own virtual clusters or pools, as we call them. So you can see we've got the CMS and Atlas projects up here. See, Fermilab has its own. GLOW is the pool that the University of Wisconsin operates for its local researchers, LIGO, and some of these other physics projects that some of you may be a part of or may be involved in supporting. So this includes, like I mentioned, the groups that did many millions of hours to help with the discovery of the Higgs boson and confirm the measurement of the Higgs boson. Large collaborations with multiple institutions collaborating, multiple researchers at multiple institutions, including the LIGO collaboration and some others who have studied gravitational waves, the source of another Nobel Prize recently measuring the merger of two black holes. But that power is brought to the fingertips of individual researchers across campuses through the Open Science Pool, which is that third highest ranking pool in the computation delivered through the OSG technologies. And it's a pool operated by core OSG for, like I said, single researchers and groups. They can have access through the OSG Connect access points that we operate that come with data staging and documentation and facilitation. Smaller multi-institutional collaborations rely on the Open Science Pool instead of operating their own pool using OSG technologies. And campuses can have their own access points into the Open Science Pool as well, serving what may be a really diverse research community instead of necessarily being part of a multi-institutional collaboration. And given that the resources from the Open Science Pool are effectively donated, often in sort of a backfill way from clusters across all of the institutions that support it, the compute tasks that run on the OSG need to be not just high throughput, but of a particular shape and size on a per job basis so that they can run and not be subject to the rates of interruption that would actually make throughput worse. And additionally, because it's a large distributed system, there are things about running computational tasks in OSG, like because it's so distributed that you can't rely on there being sort of a single shared file system. Data actually needs to be moved around, and the compute system and Condor, the scheduler, make that possible. Additionally, compute tasks run best if they're using open source software that can be made portable in some way, even if through containers, because there isn't sort of some single place to install software and guarantee that it's accessible across all of the different sites that make up the Open Science Pool. So the ideal jobs that we talk about, where a user can have literally up to 10,000 cores in use within hours after submitting, are jobs that individually need a single core, run for less than 10 hours, need a laptop amount of memory, and less than a gigabyte of input and output with highly portable software. The OSPool can still be really advantageous with up to hundreds of cores in use concurrently for jobs that are up to 8 cores in size, up to as much as 20 hours, but you really don't want to go longer than that just because of the rate of potential interruption from the fact that your jobs are backfilling other sites. But with some big data handling tools and caching across the Open Science Grid that will be covered in Friday, we can support jobs with up to 10 gigabytes of input or output as well. And on Thursday, we talk a lot about different strategies for supporting various types of software, but generally if it's open source, it's really difficult for us to meet a software that can't be supported on the Open Science Pool by one of the major strategies that are taught on Thursday. Make sure to check that out. Going back to our concrete example where we had 12,000 core hours of brain images to process, I just wanted to compare a little bit here in sort of a hypothetical based on what we kind of typically see across even our local computing systems at UW-Madison. But On a good day, if somebody was running lots of 40 core jobs on our MPI capable server, because our servers there actually have 20 cores a piece in the largest set of them, they might get several of those running within the first day, but they probably won't reach their peak in terms of number of total jobs and number of total cores for up to several days. And for larger jobs, it may take several days for those to start. But running that same work, if it can be executed as lots of single core tasks, literally within just a few hours after submitting, we see people reaching a peak of hundreds of cores in use. I mentioned 600 before as something we've seen in our local HTC system, where that entire set of 12,000 hours of work could be completed before, with an HPC approach, you could even sort of reach a practical peak in the number of total cores. And it's the area under these lines that represents computational throughput. Now let's factor in the open science pool. And we're not even talking about 12,000 hours anymore. That literally can be achieved within just a few hours, the whole set. But if you've got enough work to do and you queue it up, within hours, you can have, like I said, thousands of jobs running and therefore thousands of cores in use. And the area difference under that curve, the amount of computational throughput and therefore research impact, changes in such a way that researchers, hopefully like many of yourselves, can start to think about their science differently. It's not just that they can do more work, but that they might be able to answer more questions at the same time with their computational work, consider more variables or factors that explain a research phenomenon they care about. And that's really what we're pushing for with the Open Science Grid, is to achieve research transformation, not just helping people, even during the school, running the work they walked in the door with, but helping them think about what they could do next. So I already mentioned some of the content. The way that the school is organized is such that in this virtual format, we split it up as sort of 2 half-time commitments over 2 weeks. In the first week, we deliver a core set of lectures that in the on-site version of the school really dominates for the first 3 to 4 days, and with lots of hands-on exercises, many of which are included in the virtual format. We're delivering these twice a day, and this year, the afternoon lectures like this one are presented publicly or via registration for people other than the selected participants that went through the application process for the school. So many of you in the room right now, I think, fit into that situation. For selected participants, the second week has some bonus topics on Monday and Tuesday, a showcase where we have researchers come and talk about the impact of high throughput computing on their own work and what sorts of transformations they've achieved, as well as some lightning talks from our participants if they want to share how their computational work is suited to a high throughput computing approach and what they're planning to do. So if you're interested in that full experience, consider applying next year if you're not one of the selected participants for this year that gets the full experience. And next year, we're hoping again that we'll be able to do an on-site experience, which is the week-long full-time commitment taking place in Madison at the University of Wisconsin. And I just want to leave with one more thing, because I know there are some research computing staff in the audience. I wanted to point out that OSG provides not just resources for researchers who can access the open science pool through the OSG Connect access points, but also directly to organizations that support researchers and collaborations so that they can share local resources into the open science pool. The NSF is requiring this actually for some forms of funding to fund local clusters, that a portion of your resources are shared outward, and OSG is mentioned as one of the ways to do that. We offer that campuses can have their own local access points or submit points, whether into the open science pool or into a collaboration that they support researchers who are part of. We have helped a number of campuses build local HTC capacity, whether they're adding HTC to their repertoire of HPC computing options, or if they're building computing resources for the first time on their campus. And then, just like the OSG school, we give a number of presentations and trainings throughout the year, including at conferences, especially where research computing professionals are likely to gather. So make sure to check some of those out. We were at PERC 21 just a couple of weeks ago, delivering a training on high throughput computing on OSG and HTC facilitation that supports that. And with that, I will take questions